Okay, so I'm Susant Acharya. I work at Robinson Research Institute in Victoria University of Wellington and in New Zealand. So in this talk, I'm going to present how we used ionic liquid gating technology to control the magnetic anisotropy in our magnetic tunneling junction thin film stacks. So the main motivation behind current work is that the magnetoresistive sensors that we get in the market, they have its limitation in some sense that it can sense only in one direction. So in this project, we want to build a sensor whose sensing axis can be actively oriented in all three axes during the measurement. And how we are going to achieve that? That can be done through the voltage control of the magnetic properties of the thin film stack comprising the sensor. So it can have a lot of application. For example, non-destructive testing for detecting deterioration in pipes, for example, or reinforcing bars in concrete, in reliability monitoring, or sensing faults in high voltage lines. So for this purpose, how we are going to make the sensor is we make the magnetic tunneling junctions. So the magnetic tunneling junction, as you know, it consists of an insulating layer that is sandwiched between two ferromagnetic layers, and one of the layer is pinned, that is called the reference layer, and the one layer is free, and that is called the sensing layer. And when the two ferromagnetic layers are in parallel direction, the resistance is generally low, whereas they are the spin orientation are in opposite direction, then the resistance is high. So changing the magnetic direction of the reference layer for the active control of the sensing layer, that is the main idea. As we know that the magnetization direction of the reference layer is based on two things. One is the interfacial energy from the exchange interaction, and the second thing is the magnetoelastic anisotropy from the strain within that reference layer. So basically, we are going to tune the magnetization property of the reference layer in this experiment. So for this purpose, we mostly use photolithography and a high vacuum deposition system to deposit the thin film stack. Then we annealed at 300 degrees centigrade, and the characterization was mostly done using the magneto-optic core effect, MOG. So most of you are familiar with magneto-optic core effect, but it basically, when we put a polarized light on a magnetic thin film and we analyze the reflected light, and based on the spin orientation of the thin film, we get contrast image contrast. This magneto-optic effect, it can be used in two mode. One is the polar mode and in longitudinal mode. In polar mode, we generally measure the out of plane field, and in longitudinal mode, the in plane field. So for this experiment, we mostly used this thin film stack, which consists of tantalum, MgO, and CoFab, a thin layer of CoFab, 1.6 nanometer. We used a heavy metal, tungsten, to induce a perpendicular anisotropy, and then we kept it with a tantalum 2 nanometer. On top of this, we drop a ionic liquid, that is DEME-TFSI. So this is a long name. So anyway, but the purpose, and then we apply the voltage on top of the thin film and the top of the thin film layer and top of the ionic liquid. We apply the voltage and see how the magnetic anisotropy changes. In the Princeton state of this thin film stack, you can see that the anisotropy is in out of plane direction. If you look at this polar MOC, it clearly the anisotropy is in out of plane direction. So then what we did is we apply a voltage at an interval of 0.5 volt with 0.5 interval, and we waited for 5 minutes, and we saw that the gradually the corrosive field is decreasing. So if you look at the right side image, when we apply a voltage of plus 3.5 volt, the corrosive field decreased almost 50% from 93 oyster to almost 51 oyster. To change the anisotropy completely, we have to apply a higher voltage. So to do that, you can see that this is the this is at 0 volt. The polar core signal is represented by the pink line, and the longitudinal smoke signal is represented by the blue line. So clearly the anisotropy is out of plane direction at 0 volt. But when we apply a voltage of plus 3.5 volt, the anisotropy now changes completely to in plane direction. Again, when we apply a voltage of minus 3.5 volt, the anisotropy changes back to the out of plane direction. And finally, when we leave the stack as it is at 0 volt for few hours, then it comes back to its pristine state. We were able to change reversibly from the in plane to an out of plane anisotropy almost 10 to 15 times and it is very much reversible. To measure the switching time of the anisotropy change, first we saturated in the out of plane direction to the thin film stock by applying a saturation magnetic field of 75 oyster. Then we did the time dependent Moog measurement, and we found that it took almost 45 seconds to change the anisotropy from out of plane to the in plane direction. On the other hand, to change the anisotropy from in plane to out of plane direction, it took almost 25 seconds. So this shows that the out of plane anisotropy is the preferred orientation of our thin film stock. So this experiment is really recent, so we have yet to definitely know how this mechanism works, why the anisotropy is changing, but we have some idea. So one possible mechanism is that when we are applying a positive voltage, for example, the negative ions are accumulated at top of the thin film, top of the ionic liquid. As a result, the positive ions are accumulated at the bottom of the ionic liquid. And this can create a very strong electric field, and the oxygen ions, they can get sucked into the top of the surface. We know that the perpendicular magnetic anisotropy in COFEP stack is due to the interface between the tungsten and COFEP. That is because due to the shape anisotropy, COFEP always tries to show the in plane anisotropy. But when the COFEP thin film is really thin, like 1.6 nanometer here, the interfacial anisotropy overcomes that shape anisotropy, and the anisotropy becomes out of plane. But when the interface get disturbed by the ionic liquid, because the migration of the oxygen ion, now the thin film stack become in plane. On the other hand, when we apply the negative voltage, again the oxygen will migrate back to this interface, and we get to our previous pristine state. So in conclusion, when we apply voltage at an increment of 0.5 volt in our ionic liquid getting stack, we were able to decrease the corrosive field significantly up to 48%. On the other hand, when we directly apply a voltage of plus or minus 3.5 volt, we completely change the anisotropy from in plane to out of plane direction. The switching time of the anisotropy was also really low. It is less than 1 minute for both the direction, and that should be sufficient to use for the application of the magnetoresistive sensor. The switching of anisotropy is volatile, but it is repeatable by applying the same gate voltage as we have seen previously. Thank you so much for your attention.
Thank you, Susant, for your interesting talk. Does anyone have any questions for Susant?
Hi, Susant. I've got one
Hi.
question. Thank you for the excellent talk. You mentioned that you tried to kind of test the fatigue of the switching between the two anisotropy directions earlier. And you tried doing it, say, like 10 or 15 times, and it was completely fine. Do you think you could like apply some sort of AC signal to test it 100 or 1,000 times, or would the kind of slow switching between the two states kind of prevent that from working?
Yeah, so that's a really good question. So I feel like if we can apply a AC signal, if the frequency is really low, then it may be possible, because the switching time was almost, as you say, 45 seconds. That's quite long. It is not like instant. So if the frequency is very low, then I think it is possible. We have not tried that, but I think this is a good suggestion. Oh yeah, we should try
One
that.
follow-up. Does the switching time change if you increase the voltage that you apply, or is it kind of always just going to take that long?
Yeah, the thing is, we were really worried that we may break down the thin film stack. That's why we didn't go higher than 3.5 volt, but we may try that one next time around.
Oh yeah, I've had the same problem before, actually, constantly breaking down the electrodes. It's so annoying.
Yes.
Thank you.
Thank you. Yeah, we can talk this about, because you have already done this kind of experiment. So I'm happy to talk further. Thanks.
We have another question for you on the chat by Usama. Please elaborate a little more about applications for your work.
Yeah, so actually, this is part of a really big project. So that's why I just only explain only a little bit of it, because I wanted to focus only this part. But the other part what we are doing is we are making this magnetic tunneling junction stacks for the sensor application. So in the magnetic tunneling junction, as you can see here, we have a reference layer and a sensing layer. So we want to tune the magnetic properties of the reference layer, the anisotropy. If we can change that, then based on that, we can also tune the sensing direction of the sensor. So that is the main idea behind this work. So here, as you can see, the thin film stack that I am using, it is just a half stack. It is not a full magnetic tunneling junction, but here we were able to show that we can tune the anisotropy of this half stack, and we want to incorporate this one in the full stack, and then we apply voltage and sense the sensing direction of the sensor. Sorry, change the sensing direction of the sensor.
All right, so Usama, I hope that answers your question about techniques we want to elaborate a little more. So I have one more question for you. So the remagnetization from in-plane to out-plane sounds like the implementation of a two-dimensional system right now.
Yeah.
Has it been possible to implement a truly three-dimensional spatial magnetic anisotropy distribution system?
That's a really good question. So this technique can be used to change only the theta direction from out of plane to the in plane, but for the phi rotation within the from x and y direction, we cannot use this technique. For that, what we are doing is we are depositing our magnetic sensors on a piezoelectric substrate and applying voltage, and that is another parallel experiment that I am doing at this moment. For that, we apply the voltage in piezoelectric substrate, and due to the strain of the piezoelectric substrate, you can change the anisotropy in plane. So basically, this is a big, as I said, this is a big project. We are just now doing like small parts where we can show that we can tune the anisotropy in different direction. Then hopefully in few months we will incorporate everything in a full magnetic stacks, sensor stack, and we saw that is possible. Thanks. Yeah, that's a really good question.
Thank you for your answer. I hope you will be able to achieve this in a few months' time. I look forward to hearing about it. Okay, so
Thanks.
do we have any more questions for Susan? If this is it, then thank you, Susan, for your really interesting talk. Correct?
Welcome.